So you're probably familiar with the concept of symmetry, right? It's sort of this idea, maybe you have a vague sense of illustrated here that if you have something drawn on a piece of paper and you fold it, like both sides will match up exactly, right? As we can see here with this kind of curved shape. On the one side, if you were to fold those over that center line, they would match exactly. On the asymmetric one, the one that's not symmetric, if you were to fold those, they wouldn't match exactly. There's a sense of evenness to the whole thing where it's balanced perfectly on both sides of some central dividing line. And this is something we see all over the place, right? We see this in nature, right? The classic example is probably a butterfly, where if you were to draw a line down the center of the butterfly and fold it over, the wings would match up perfectly. We see this in all kinds of examples in art, where we've got this crazy mosaic here, or these two swans here. We see this in photography, and we even see this in architecture and probably so many other places in our day-to-day lives. And so it's probably no surprise really that we might come across the concept of symmetry in math as well. And that's really what we're going to explore today in this video. In particular, two types of symmetry. And we can see these when we graph functions. The first one we call even symmetry, the second one we call odd. So what does that mean to be an even symmetry or an odd symmetry? Well, we have formal definitions for these, but they will also correspond with the visuals that we can see on a graph that will look a little bit more like the symmetry that we're familiar with. So first, we'll say that the function f, and again, that's just our name for this particular function. We're just talking about any arbitrary function here. An arbitrary function f is an even function if f of negative x is equal to f of x for all values of x. So for any value of x that we plug in, if that's also going to give the same output as the negative version of that, so negative x and x being two different inputs giving the same output, then this is going to be an even function. Now, just even looking at that formal definition, this may not mean a ton to us in particular just yet, but since we tend to associate symmetry with visuals, let's tie this into how this might look on a graph too. So when we say a function f is even, what we're really saying is all of the negative inputs equal all of the positive inputs, so the function is going to be symmetric over the y-axes. In other words, the graph of an even function, is symmetric about the y-axes, And of course, it's going to help to actually see this. So let's look at a few different examples here. We've got three graphs. Each of these represent an even function. That's because if we were to draw a line down the center, right along the y-axis here, we would see that this indeed matches on both sides of that line. Right? This right-hand side of the y-axis and this left-hand side of the y-axis are essentially identical. If we were to fold our hypothetical paper down that center line, then those two curves in blue on either side of the line would match when we do that. And this would be the same with this function here and with this function here. Now this piece isn't terribly important just yet, but this represents a y is equal to x squared, or a variation of y is equal to x squared. This represents a variation of y is equal to the absolute value of x, and this represents a variation of y is equal to cosine of x restricted to a certain domain. Those details aren't terribly important yet, but this is really just to give some examples of what types of functions might be even, as we can notice based on the shapes of their graphs. Now, on the other hand, we would say that a function f is odd. The function f is an odd function if f of negative x is equal to negative f of x. So it's even if f of negative x is equal to f of x, and it's odd if f of negative x is equal to negative f of x. Now again, this might not mean a ton to us just by looking at the equations themselves, but if we kind of step this back and think about what this means visually, that'll give us a better sense of how this is symmetrical. And so when we have an odd function, we'll say that the graph of an odd function, is symmetric about the origin. And just as a quick reminder here, the origin is the point 0, 0 on our graph. It's that like very center point where the y-axis and the x-axis intersect. And we can see some examples of odd functions as well. Now, just looking at these, it might not be as immediately obvious quite how they're symmetric, right? This is less about if we were to fold the paper together and getting them to match, and more about requiring multiple folds. Or perhaps a better way to think about it is a 180-degree rotation. For instance, if we look at this graph here, and I was to duplicate it, and then rotate it, we can see that as I rotate this 180 degrees, so halfway around a full circle, it ends up matching up with where we started, right? So a 180-degree rotation is going to get this to match where we started, and so that's what we mean when we say an odd symmetry, right? An even symmetry is matching the left side to the right side as if we were going to fold them together. A odd symmetry is if we were going to rotate our image 180 degrees and get the same thing that we started with. Similarly, and this is a little bit harder to illustrate in a two-dimensional space like a video, but if we were to fold part of this down and then fold it over, those pieces would have to match. In other words, this piece here has to match this piece here, flipped twice. But again, that's a hard thing to illustrate in a video where we're watching this in a two-dimensional plane. So it may be easier to think of it as a 180-degree rotation. And these two functions here are going to be sine of x on a restricted domain and y is equal to x cubed. Again, the specifics of those equations, we don't need to worry about them just yet, but those are just to give a sense of like what types of functions might be even or odd and how we can see that visually. So identifying this visually is one thing. We've got a lot of practice by looking at things in art and nature and photography, etc., to see those types of symmetries with our eyes. But how can we look at an equation and test for whether or not it's going to be evenly symmetric or odd symmetric or maybe neither? Well, essentially what we're going to do is utilize the definitions. In other words, we defined an even function by when f of negative x is equal to f of x. And we defined an odd function when f of negative x was equal to negative f of x. And what we can notice here is that both of these definitions are based around f of negative x. So if we want to test for whether it's even, odd, or neither, we can evaluate or simplify the expression for f of negative x and see, does it equal f of x? Does it equal negative f of x, or maybe neither? And so what we'll need to do is we'll need to simplify the expression f of negative x and ask, is it equal to f of x? If so, that means it's even. Is it equal to negative f of x? If so, then it's odd. And if neither, then neither. If we can't get it to equal positive f of x or negative f of x, then we know it has neither of these symmetries. And so let's try this out in a few examples. Let's see if we can look at a function and just based on the equation, without even graphing, we can determine whether or not it's even, odd, or neither. And so we'll look first at x cubed minus 6x. Remember here what we're looking to do is find out whether f of negative x is equal to f of x or negative f of x or neither. And so what we can do is we can plug in negative x into our function. And so f of negative x means we're going to take this input and substitute it in for every instance of x in our equation. And so we'll take negative x, and we'll be careful with our parentheses, but we'll take negative x and plug it in for x cubed in this case. And so we have negative x, the quantity, cubed, minus 6 times negative x. Now, if we were to simplify this expression out, negative x cubed is negative x times negative x times negative x, and 3 negatives will give us a negative, and so we have negative times x cubed. Minus 6 times minus x means 2 negatives will make a positive, and so that's going to give us a positive 6x, giving us an expression of negative x cubed plus 6x. Now you might be saying, well, that doesn't look exactly like what we started with, and that's true. But there is something that we can do here that's a little bit clever that's going to allow us to get this to match either negative f of x or f of x, and that's to factor out a negative sign. So if you think back to your algebra class, you might have worked a lot with factoring. We're going to utilize some of those tools here to help try to get this expression to match up with either f of x or negative f of x. And so we'll factor out a negative 1. If we factor out a negative 1, we're going to have negative 1 times the opposite of negative x cubed, so x cubed, and the opposite of plus 6 squared, or excuse me, of plus 6x, or minus 6x. And so here we have negative 1 times the quantity x squared minus 6x. Now that quantity x squared minus 6x, that should look kind of familiar, right? Because that is our expression f of x. And so what we've actually shown here is that we've got negative 1, or more simply negative, times the quantity, which is f of x, which is our function f of x. And so we have negative f of x. And what this means is that f of negative x is equal to negative x, thus satisfying our definition of an odd function. And so we can say, therefore, f of x is odd. Again, because f of negative x is equal to f of x. Right, so without even graphing this, we're able to determine the symmetry simply by plugging in negative x into our function and observing that in this case, it's equal to negative f of x. We can take a similar approach here with g of x. If we plug in negative x into g of x and then see if this either equals positive g of x or negative g of x, we'll be able to determine its symmetry. And so if we plug in negative x here, we're going to have 2 times the quantity negative x squared plus 3. We know when we square something, we multiply it by itself. If we're multiplying a negative x times a negative x, that's 2 negatives, so it will make a positive, giving us 2x squared plus 3. And as we can see here, this function here is the same as this here, and so this matches g of x. And so we have equal to g of x. Because g of negative x is equal to g of x, that clues us in that this is an even function, and so we can say, therefore, g of x is even. And again, this is because g of negative x is equal to g of x. And that's what it means to be an even function. That's how we defined it. And so it satisfies that definition. Finally, let's look at h of x, which is equal to 2x cubed minus 3x squared. We can apply a similar process here as well, plugging in negative x into h. If we do that here, we'll substitute every instance of x with negative x, and so we have 2 times negative x cubed minus 3 times negative x squared. If we are cubing a negative number, that's going to stay negative, and so we'll have negative 2 times x cubed. I'm just moving the negative out front to make it look a little bit neater, but 2 times negative x cubed, or negative 2x cubed. And then here we have minus 3 times negative x. Ooh, I wrote this wrong. Let me correct that here. Negative x, the quantity, squared. There we go. Let's make sure we get that right. We've got negative 3 times negative x, the quantity, squared. And negative x times negative x is two negatives, which will make a positive. And so we have negative 3 times x squared. Now, this here doesn't look exactly like h of x quite yet. And so we might try that same trick of factoring out a 1. Let's try factoring out a negative 1. And if we do that here, we'll have negative times the opposite of negative 2x cubed, which is 2x cubed, and the opposite of negative 3x squared, which is positive 3x. Except again here, this doesn't quite equal this, right? And this doesn't quite equal this either. So in neither of these cases do we have h of negative x equal to h of x or negative h of x, right? So since, we'll say since h of negative x does not equal h of x, and h of negative x does not equal negative h of x, then h is neither even nor odd. And so this function doesn't have either of those symmetries. Now, I'll give you a little bit of a bonus tip here. If you've been paying really close attention and looking closely at the exponents on these, you'll notice in this case in particular, we have a combination of an odd exponent and an even exponent, and that one worked out to be neither. In the previous example, we just had an even exponent, and though there's no exponent listed here, if we remember the fact that x to the 0 is equal to 1, we can effectively say that there is an implicit x to the 0 here, 0 also being an even number. And so we have only even number exponents, and our function is even. And then if we look back at our first example, we have an odd exponent, and this one again is not listed, but implicitly it's a 1. And so we only have odd exponents here, and our function is odd. So if we're looking at a function, and I should be clear here, this is specific only to polynomial functions, so only functions that look like this. When you add in sine or log or square roots or things like that, this rule doesn't really apply anymore. But if it's just polynomial functions, if all of the exponents are odd, the function's going to end up being odd. If all of the exponents are even, the function's going to end up being even. And if you have a mixture of some odd exponents and some even exponents, then it's going to have neither of the two symmetries. Hopefully that bonus tip was useful. Again, make sure it's only applied to polynomial functions because it doesn't necessarily continue to work when you look at other things. But hopefully you find that useful, and hopefully you found this whole video useful. And thinking of symmetry in terms of math can give you kind of a bigger perspective or better sense of how mathematics can fit into the rest of the world that we live in. Anyways, if you do have any questions, please don't hesitate to reach out. I'm always here to help, and I hope you have a great rest of your day.